Now let's consider another way of looking at velocity as a rate in terms of the example that we see here. If we have a displacement of -8 meters in 4 seconds, what is the average velocity? Now, average velocity is what? It's the average rate at which position changes, which is going to be change in position per unit of time, the number of meters per second. So we can intuitively say a -8 meter change in position in 4 seconds is an average of -2 meters per second. Okay, so that's -2 meters per second on the average, so that the average velocity should be -2 meters per second. Another way of looking at it, in terms of the units, it's really not another way, just another way of writing the calculation. We divided the 8 meters by the 4 seconds to get the 2 meters per second, or the -2. So if we divide -8 meters by 4 seconds, we get -2 meters / second, because the meters are divided by seconds here, and meters are divided by seconds here. Okay? In the more formal equation for the rate, we see that the average velocity is the average rate of change. It's the time rate of change of position. Delta S is the change in the quantity, which is the position change, which we also call displacement. And notice we have a negative displacement here. Distance can't be negative, displacement can. That's the difference between distance and displacement. Okay? Distances are always positive, but displacements can be positive or negative, for example, to the right or to the left. And the time duration, delta t. We know then that the rate is the change in the quantity divided by the time duration. And that gives us the same calculation as before. The -8 meters divided by 4 seconds equals -2 meters per second. Okay, we have a picture. Let's look a little more closely at the picture. We can think of the 8 meter distance as being represented, or displacement. Let's say that again. The -8 meter displacement, and there shouldn't be a double arrow on that. That should be a single arrow. It's a -8 meter displacement, which we'll think of here as a displacement to the left as opposed to the right. And we imagine 4 seconds corresponding to the 8 meter displacement. Well, every one of these seconds corresponds to -2 meters. And of course we can make the same type of diagram as before. This time the delta S and the delta T are known, and we use those to get V. There's a third case. And we'll have to zoom back and take a look at it. Okay, the question is, how long does it take to get a displacement of 40 meters if we're moving at an average velocity of 8 meters per second? Well, in an average of 8 meters every second, which is what 8 meters per second means, how long is it going to take to go 40 meters? Every second we get 8 meters, we got to get 40. Obviously it's going to take 40 divided by 8, or 5 seconds, to travel the 40 meters. So this is a way of directly reasoning the situation. To write the calculation in terms of units, we divide 40 meters by 8 meters per second. The 40 here was 40 meters per 40 meters. The 8 was 8 meters per second. Now we get the 40 divided by 8, which is going to give us 5. And we got meters divided by meters per second. And what's that give us? Well, let's be careful. Meters divided by meters per second. When you divide, you invert the denominator and multiply, right? So take the denominator and invert it, we get seconds over meters. The meters that we have here, we'll write meters over 1, just so we have numerator to match numerator and denominator to match denominator. The meter divided by the meter is going to cancel out. Second divided by 1 is just second, so we end up with 5 seconds. In terms of rate quantities, the delta S is going to equal the product of V average and delta T. Okay, we multiply the average rate by the time because the rate is the change in quantity per unit of time. We multiply that by the number of time units and we get the change in our quantity. Okay, that's the intuitive version of this equation. Of course, that version doesn't apply directly to the situation where we want to, where we're given the displacement delta S and the rate V average. So in order to solve for delta T, we're going to divide both sides of the equation by V average, and we're going to notice that I've written this down backwards. Don't be careless like I am. This should read delta S divided by delta T. Okay, because obviously when we divide both sides by V average, we get delta S over V average, and that'll equal our delta T. I often, when I do something like this in class, when I just simply write something down backwards or upside down, I'll tell my students that I've done that just to see if they were really paying attention. But it's not true. I just honestly make those mistakes. I almost never do something deliberately wrong. So if you see a mistake, blame me for it. Okay, anyhow, delta T is delta S over, still got it wrong, and that wasn't intentional either. Delta S over V average. Okay, so delta T is delta S over V average. What we get when we divide both sides of this equation by V average, that's going to be 40 meters over 8 meters per second, which is 5 seconds, as we've seen. Let's just look at the situation with velocity, time, and displacement. Okay? In general, for constant velocity, and really I should have average written in all these velocities. Okay? That's average, that's average. Okay, I won't write it on these down here, but you understand that these are average velocities that we're talking about. Okay, this is pretty intuitive, that your displacement is your average velocity multiplied by your time interval. The intuitive aspect of that is simply that the number of meters we move is the number of meters we move per second multiplied by the number of seconds. Just like the number of dollars we make is equal to the number of dollars per hour times the number of hours that we work. We can rearrange this equation in this intuitive form, and we divide both sides by delta T here, and we quickly get an expression for V average, which is delta S over delta T. Now this one is usually taken as the definition of velocity. Since I find that the most intuitive thing people understand is how much they get paid, if they know how much they're paid per hour and the number of hours, I usually start with rate relationships in this form. But there's nothing wrong with this form either, because you know that the number of dollars you get paid is the number of dollars, the number of dollars per hour is the number of dollars divided by the number of hours. Both of these are very intuitive, especially in terms of dollars and dollars per hour. And they should be equally intuitive in terms of any kind of rate. The change in the quantity is the rate times the time interval. The rate is the change in quantity divided by the time interval. If we take the equation and solve it for delta T, we get the equation that I should have written right on the previous page. Delta T is delta S over average velocity. In terms of velocities, this one is just a little less intuitive than these. In terms of pay rates, of course, everybody being interested in money has no problem, no matter how it's stated. And then we have our relationship triangle here, where any one of these quantities can be obtained from the other two. And here are the relationships that we've just obtained above.